No, I got to be careful because with the mic on, my voice keeps getting louder and louder, and the audience starts getting headaches, and that's not good. It's a pleasure to be back in Japan, in particular in Tokyo. This is my fourth or fifth trip, I guess, to Tokyo. And it's been good so far. I had the privilege of visiting Professor Harik. Damn it, I'm screwing up already. Jet lag is just doing a number on me today. Hiro Nori Kasahara. Good. Kasahara-san, visiting his lab. There's no question the last bullet on this title slide is correct. He is absolutely committed to a sustainable planet so that some of you young people might even be able to enjoy the planet when the next century arrives. I don't know whether I will. I'm working at it, but we'll have to see. He has, using the compiler, using various granularities of parallelism, he's been able to get good power usages. So he's reduced the amount of power required in a substantial way. And he has not lost face with performance. You know, people who say that performance doesn't matter are just bullshitting themselves. Everybody wants performance. If you didn't care about performance, you could build an ALU with just a simple full adder and a latch, and then bit serially 64 cycles, and you would get A plus B. But that's not the name of the game. The name of the game is how do we do performance at the same time we're reducing the power consumption. And I got a bunch of slides to show you of cases where you may want to investigate. I was at the first ISCA in Australia. In fact, Wenmei presented our first HPS ISCA paper at ISCA in 1986. That was more than a couple of years ago, I guess. And I have fond memories of that ISCA, and this one looks like it's taking off to be just as good, if not better. Mario Tokaro was the program chair. My favorite Japanese friend, who used to come to the U.S. during the summer, and he and I used to consult for the same government agency. And then he'd go back at the end of the summer, and eventually he got married, and that was the end of his trips to the U.S. His name was Hisao Yamada-san, a senior professor at Tokyo University. So, is there anything else I want to do before I get started talking about what you want to hear? Yeah. So another good friend is Watanabe-san, the chief microarchitect of the supercomputers by NEC. And I haven't seen him in a while, and I'd like to see him again. Finally, this year, so I've been waiting every year hoping that the Eckert-Markley Award winner will be Andrei Seznek. And this year it has happened, and I'm delighted that it's happened, and I'm looking forward to the awards ceremony tomorrow where he's going to have some things to say. Okay, enough of my meandering before the... I haven't said anything yet. Why are they clapping? I never understood clapping before the talk, you know? Because maybe what they do is they clap, and then after the talk, they wish they hadn't. You know, maybe that's what goes on. Okay, so my talk, and then we're going to follow that with a panel dealing with sustainability. The title of my talk, What Problems with Solving the Sustainability Problem? What must come first, what must come second, and then third? And first and second has nothing to do with computer architecture. So let's move along. So here's the outline. Obstacle 1, obstacle 2, obstacle 3. Obstacle 1 is you got to admit that there is a problem. You know, I know a university where they're ranked 9th among universities doing computer architecture. And they'll never get higher than 9th because they always insist they're number 1. In fact, they'll probably drop to 10th, 11th, 12th, etc., because there are other universities that are ranked 10th, 11th, 12th, and 13th, and they want to be ranked number 1. So there's no way to solve a problem unless you first admit that you have a problem. So that's the first obstacle, nothing to do with computer architecture. And I just told you about the school, so I just promoted them to number 9. You get the point. The Yangtze River, if you've never been in China, used to have these 3 gorges, and you could take a boat along the Yangtze River. It was spectacular seeing the 2 mountains on either side of you as the boat navigated the river. But then the Chinese government decided that they need energy. And if they create a dam at the end of the river, then they will get a great source of hydroelectric power, and they will satisfy 10% of their energy requirements. So they put in the dam. What happens when you put in a dam is the water level raises, and now those beautiful mountains that you would sail between is all underwater. So if you haven't been to the 3 gorges, it's too late. And after they completed the dam, they did the measurements and the analysis, and they discovered that instead of 10%, it's only 1%. And so you say, well, what was wrong with those engineers that did the calculation in the first place? Nothing. It's that the amount of energy required is grown by a factor of 10. And that should scare the hell out of you. It scares the hell out of me. Little anecdote, 40% of icebergs will be gone regardless what we do. So the ice cubes will melt, raising the sea level, and will we have humans on the planet in the next century? Data center computers use, so this is also scary. Data center, another anecdote, use 27% of peak power when they're just sitting there twiddling their thumbs. Even green advocates argue about what's more important. The embodied energy savings, which is everything that it takes to make your laptop, getting the ore out of the mountainside, getting it down to metal, sending the metal to the factory where they're going to make it, and that's what's important. And the other group says, no. What's really important is the operational use of all the energy. And so they have that, what's important is what we're doing. Silly. And should be, forget it. They're both important, and we have serious problems. Okay, so much for obstacle number 1. Obstacle number 2, willingness to do something about it. There are people out there who say, yeah, sustainability is important, but I'll be dead by the time it really matters. Next century, no more people, that's okay. I won't be around, so why should I care? And I can take advantage of the energy that is available right now. And so you have to want to do something about it. One of the problems, and I'm finding this in the university since COVID, is the entitled affluent problem, I call it. The student doesn't want to study, doesn't do well on the exams, comes into my office after the exam and says, I want an A. You want an A? Did you earn an A? Why are you asking me irrelevant questions? You're a state employee. You're paid by the state of Texas, and my father is a taxpayer, so do your job, give me an A, the entitled. The next bullet, I enjoy spending, really wasting, energy in Hangzhou. So I don't know how many of you have been to Hangzhou, but it used to be that this was barren land, and now it's an industrial center. And after dark, they turn on, I don't know how many thousands of light bulbs, consuming energy, so that you can go there and go, wow, it may cost us the planet, but in addition to saying there is a problem, we have to be interested in solving it. The laziness problem. We'll all be dead by then, why should we bother? Don't worry about the future. The uphill battle problem. Yeah, I'd like to do something about it, but I can't convince anybody else, and I don't like being the only one because I won't be effective, and so therefore I'll do nothing. So all these have to do with doing something about it and having the willingness to do something about it. In my country, we have a problem going on right now with a lot of people who should know better keeping their mouth shut. And as long as they keep their mouth shut, the problem that I don't want to get into because it's a little political, and it's a lot political in nature, but the problem is not going to get solved. But who am I? I'm just one person. I can't do anything. Wrong. One person can do something, get somebody else interested. Before we know it, maybe we can get past obstacle 2. So now we're at obstacle 3. If we do these two things, which could be done, have nothing to do with architecture, we're ready for obstacle 3, which is what can computer architecture do? And for that, I've got a number of bullets that I'm going to spend a couple of minutes each on, telling you something about what you can do as a computer architect that could turn the corner on this thing that's out there that says that by the next century, beginning of next century, there will be no human life on the planet. And that's real. I'm not saying it for scare tactics, I'm saying it for real. Okay, so we now talk about all of these. So HPS checkpoint. HPS happens to be the acronym that I've used for me and my students doing research in microarchitecture, out-of-order execution, branch prediction, and all that stuff, which has been going on now since 1985. So it's what? It's 85 is 40 years ago is when we started. And so designing the microarchitecture for an HPS machine, we're very conscious of mispredicted branches. We predict a branch wrong. We need to do something so that when we discover that we've mispredicted wrong, we can throw away everything since that branch showed up, and then go down the correct path. So what are we going to do? We got a checkpoint. Well, do we have to checkpoint? We need to be able to recover the state. And so what do I say? We need to recover fast on a branch mispredict. On an exception, exceptions don't happen that often, we can take some slack. But branches happen every 4 or 5 instructions. If I've got a really complex instruction set, it's probably less than 4. Probably every 3 instructions is a branch. So I got to be able to recover the state when I mispredict the branch. So we checkpointed the register file before each branch. Wow, that's good. Checkpoint the register file. When we see that the branch is mispredicted, we recover the register file since the last checkpoint, and then we can move forward. But why did we checkpoint the register file? 32 registers? How many of them got changed? So here's a branch, and here's the next branch. Within that stream, within that flow, how many registers got modified? How many destination writes were there? 3, 4, maybe 2? And yet we're checkpointing all 32. Great loss in energy, a great waste in energy. If we mispredict, we return to the checkpoint, but most registers do not get written in every block. Ergo, that's Latin for therefore, we write to 3 registers, we save 32 of them because the other 29 haven't been written, so they don't get changed at all. And we were correctly slammed by these people reading our first and second ISCA paper. What are you doing checkpointing the register file? It's a waste of energy. And they were correct. And a couple of years later, we figured out a way that we will only change those registers that got modified during that block with a big savings. So what am I suggesting? You're doing research, and you may have to take a shortcut to make the thing work, but you're not done yet. What you really want to do is do that thing. It's got to be done, and do it differently than the way you've been doing it before. The insight: find a better way to recover from a mispredicted branch. And we did. A bit vector that identifies the registers that are written. Next bullet, heterogeneity. I love heterogeneity. Why? How many papers do we see lately where they say, well, we give on performance, but we save energy? Again, nobody wants the machine to run like a dog. Doesn't work. Nobody buy it. Yes, we need to save energy, but we also need to be concerned about the performance. So the papers show, the accepted papers show, that for a little bit of performance, we can get a much bigger savings in energy. Is that good? Yeah, it's good. What's better? Being able to increase the performance at the same time we increase the energy savings. Is that possible? Yeah, heterogeneity is the answer. Now, there is one problem with heterogeneity, and that means that you're going to have to think smartly. But if we think in terms of heterogeneous cores, and if we think in terms of we're going to design this thing so the performance is better and the energy savings is better, can we do it? And the answer is yes. Well, what's the hook? Because there's never a free lunch. The hook is that when we do this, we're going to design something that is not going to be general purpose. It's going to be much more targeted, and so we're going to have to pick what we do heterogeneously, we do judiciously if it's going to work. So performance plus energy savings, but not cheap, so you need to select what to do heterogeneously. The refrigerator with the Chicago Bears. So I don't know how many of you are Americans or how many of you follow American football, the National Football League. The team that was the team in the mid-'80s were the Chicago Bears. And they had a defensive tackle on the Bears named William Perry. They nicknamed him the refrigerator. Why did they call him the refrigerator? Because he was so big and tough and strong. Defensive tackle. Unlike the game they play in other countries of the world where you have the offense becomes the defense when the other team gets the ball. In America, we have unions, labor unions. So you either play offense or you play defense, but not both. William Perry, defensive tackle for the Chicago Bears. When the offense is on the field, he's a defensive tackle. He's sitting on the bench. And what's most important about him sitting on the bench is he's powered off. Then the Bears get to the point where we're on the 1 foot line. 1 foot and a touchdown is scored. So what do? They power up William Perry, bring him into the game, hand him the ball, point them in the right direction, and there's no way the other team's defense can stop him if he has to travel this distance. So he's a defensive lineman, but when the Bears are on the 1 foot line, he becomes an offensive back, if you will. Let's see what we say about that. I thought I said more about this, and I guess I didn't. So William Perry is an example of an accelerator. I nicknamed him the refrigerator because if you go into somebody's kitchen And you look at all the things that are in the kitchen, the biggest thing is the refrigerator. So I said, William Perry is the refrigerator. Power it off when he's not carrying the ball the 1 foot. And that's the key. What can I do that is powered on when needed and powered off when not needed? General purpose code, FPGAs, or refrigerators, ASICs. ASICs provide performance and energy savings if you selected correctly. That's what I mean by judicious selection. The functions to accelerate, you can turn off the power when it's not in use. The compiler is going to have to help, because if it's going to be needed here, you need to start powering it off here, so powering it on here, so that it takes a few cycles so you don't warp the chip. Morphcore, paper done by Habib and won the Best Paper Award in Micro of 2012. He said, what we need this high-powered core. Why? Amdahl's law. My brain has gone to sleep. I've forgotten the term, but I'll just talk about it. You want to use a region of memory, a data structure, and you don't want anyone else in there, so you want exclusive use of that data structure. What's the term I'm thinking of? Thank you, Guri. See, I need my babysitter to help me out. Critical section. So you've got a critical section. They call it the code. It's not really the code. It's the data structure in memory that you've got. And you want to be able to do something and not be screwed by some other thread that gets in the way. So how do I do that? Well, I can do it with an ASIC. So what do I say here? Amdahl's law suggests high-powered hardware. I gave you that. Guri gave you critical section, which is also needed. Sometimes there is no parallelism. So what did Morphcore do? What Habib did is he designed an engine so that with pass transistors he can take that engine and run it as a heavyweight core, not as good as an ASIC, because it has to get through the pass transistors, has to connect the different pieces, but almost as good as an ASIC, if the code that needs to run does require a heavy-duty core, like the two examples I just gave. Or maybe you don't need that. Maybe what you have is like Sun Microsystems found, is thread-level parallelism. You want to be able to deal with throughput, and you're not so concerned about latency through the machine, but you're going to have to operate on all these different pixels at the same time, thread-level parallelism. Can I put in pass transistors that takes the heavyweight core and breaks it into its little pieces? Or is there no parallelism? So no parallelism says, I don't want to run anything more than I need. I've got no parallelism, so I don't want the lots. I don't have this requirement for one heavy duty, so I'll just run one of the Mickey Mouse cores that make up this heavy duty core when I need it and save energy. So Morphcore trades a little bit of performance for all targets. A large granularity FPGA, if you wish, which gives you almost the performance that you would get with ASICs in each of the three cases. And so that's another example of looking what you got. Can I do it differently so that I can get the benefit of the different requirements that the cores are going to require? Boost algorithm. So you all know that the way we implement multiply in a machine is as a sequence of shifts and adds. And on the left there, you see the classic shift and add. I've got the multiplicand and the multiplier. I take the digit of the multiplier and the low order digital multiplier, multiply it by the multiplicand, and get a piece, and add that piece to the all zeros that you got at the beginning. If you look at the below that shifter on the diagram, you run it, it's all zeros, we run it around, we add the multiplicand, we then shift it to 1 bit, so that the next time around, I am using the next bit of the multiplier. Now, if I was doing a decimal machine, that multiplier is going to have to multiply the multiplicand by 2, 3, 4, 5, 6, whatever, but I'm not. I live in a binary world where I'm multiplying that multiplicand by 1 or 0. And if you multiply the multiplicand by 0, you get 0, and if you multiply it by 1, you get the multiplicand. And so I only need one control signal to this mux telling me whether I should add because that bit was a 1, or whether I should pass the bit pattern because that bit was a 0. And if it's an n-bit data type, then I'm going to require n cycles. And Andrew Booth came up with a scheme where he said if 1 bit is a win, maybe 2 bits is even better. I can do the job in half the number of cycles. Now, it turns out if the job then became much harder if I'm doing 2 cycles, then this is a bad idea. But if I look at these 2 pictures, the one on the left is doing 1 bit at a time, the one on the right is doing, the one on the left is doing 1 bit at a time, the one on the right is doing 2 bits at a time. And now if it's 2 bits, what do I got? 0, 0? That takes the same as the classic case. 0, 1 also takes the same as the classic case. I add the multiplicand and I shift by 2 bits. My objective is to do the job not in n cycles, but in n over 2 cycles. And if the add is going now 64-bit adds, you know, Intel had a chip, they called it the, I've forgotten what they called it. What did they call it? Do you remember? The ALU that allowed you to run the ALU by breaking the number of bits into 2 parts, and you do the high order bits of one add while at the same time you're doing the low order bits of the next add. And by doing that, they've got the addition being done in half the number of cycles. If the job to do admits that, and I look at the 2 pictures here, and it does, then there's a place where I could save energy. I could look at the problem and say, how long is this going to take? And if it's going to take approximately the same, there is one place where we lose. In the case of Booth's algorithm, I need to shift 1 bit before I do the add, and then I need to shift 1 bit after I do the add in order to be able to accommodate all 4 values. 0 and 1, I do the add, I pass or add, and then shift 2 bits. 2, I shift a bit, which gets the multiplicand 1 bit over, which is multiplying by, shifting by 1 bit is multiplying by 2, and then I shift the other bit. So each iteration gives you 2 bits accomplished. 3 is a problem. That would be multiply by 2, and then multiply by 1, and then add the 2. I can't tolerate that. But the brilliant solution there is 3 has an interesting characteristic. It's equal to 4 minus 1. And so if I subtract 1 from the, I multiply the multiplicand by minus 1, and then shift by 2 bits. But what about that 4? Well, the 4 is added to the 2 bits that I'm going to shift in next, because the 4, when I move it 2 bits, becomes 1, and so I can add that to whatever those 2 bits are. So, for example, if the 2 bits are 0, 0, then I add 1, I get 0, 1. If the 2 bits are 1, 1, and I add 1, I get 0, and shift by 2 bits. So I look at these two figures and I say, there's an opportunity here, getting something done faster. Braids. So in my group, we did out-of-order execution. The fetch width was multiple instructions, and using out-of-order execution, we got big performance win at the expense of a lot of hardware. So one of my PhD students, Francis Seng, said, instead of doing an 8 wide out of order, why don't I do a 2 wide in order? We call it a braid, and I'll do 4 of them. And at compile time, I will construct these braids from the code that I've got. So the first step in the code is you go from the high-level language to some intermediate form, and then the second step in the code is to break that intermediate form into 4 braids. And so I've got these braids executing in order and only 2 wide at big savings. And occasionally I need to send a result constructed in one braid to another braid, but that occasionally is sufficiently not close together that I end up using braids, does the job at almost the same performance, but at a big savings in energy. Quantum. The claim is quantum will do better, do everything better. Don't hold your breath. Money for decryption isn't the same as money for science. An interesting paradigm, quantum is an interesting paradigm. It needs to be studied. But this business of solving tweaks in quantum, I don't know how many years before we actually have a quantum accelerator, that we have more than 2 qubits, and they can last more than 3 picoseconds, and they can run at temperatures greater than 0.4 Kelvin. The quantum people say that we'll be able to get the money to do research to improve science, to simulate chemical reactions going on. It's not clear to me that, so governments are spending a lot of money on quantum now. It's not clear to me that quantum is going to get that money when the problem that we're going to look at is going to be dealing with simulation of scientific reactions as opposed to dealing with decryption. The funding for decryption is very clear. If we're going to be a first-class country and not back in the noise, we better be able to do decryption. And that problem, the crypto people now talk about post-quantum crypto, and that is very real. So, but when will it be ready for showtime? I'm reluctant to consider it now in the world of sustainability. Page size. So I've seen lots of people talk about we need to redo the system stack, and we need to redo the way memory talks to the CPU, and we talk about the software stack. We may as well talk about the hardware stack that's underneath the software stack. And the page size is still 4 kilobytes, and we still, with very few exceptions, have been able to get people to change the page size. It requires buy-in from the operating systems people, absolutely. And yet today, so Intel has made a shot at it. They now do 3 page sizes, 4 kilobytes, 2 megabytes, and 1 gigabyte. And that's a step in the first direction. But where's everybody else? Well, ARM has also made a first step. But we need to do more. How about if we make the page size every power of 2? So Farouk Gouvenaoui did that, and it's published in this conference in 2020. And what he does is have an elegant solution for making the page size be any power of 2. That's still not good enough. It needs to be worked on some more, but it's not going to take hold until the OS people get on the bandwagon. For example, we need to revisit what this is all about. For example, 4 kilobyte page size is a good place to start. Data sets these days dwarf 4 kilobytes, huge data sets we have. Too many TLB entries, which creates a first level miss, misses in the first level TLB because there's just too many page table entries in the first level TLB if we're going to be able to handle large data sets. Simple example, suppose what I say, let's make it really Mickey Mouse. We'll say 1 megabyte, which is 2 to the 20 bytes. 4 kilobyte page size, 2 to the 12 bytes. 2 to the 20 divided by 2 to the 12 is 2 to the 8th. So if I want to have a page that's 1 megabyte, it's going to require 2 to the 8th, 256 page table entries. That's room for disaster. So that needs to be worked on. And in order to do it, the OS people have to get on board. You know, I keep hearing about the software stack, and I say, good luck. I hope we can get them on board. How? Well, that's your job, I guess. So, too many TLB entries. By the way, if I have all these powers of 2 page sizes, and Gouverneur provided the mechanism to allow it to all go in, all the sizes be accommodated by one first level TLB, and if it does occasionally, and very occasionally, result in a first level miss, I go to the second level. But very rarely does it take a first level miss if I allow each data structure to have its own size and not have to be made up of a large number of 4 kilobyte pages. Intel ARM have taken the first step. I've said that. Gouverneur, I've said that. So we're getting to the point now where maybe the base page size shouldn't be 4 kilobytes. How about making it 256 kilobytes, 2 to the 18th? Not easy. First, we need to get OS on board. Something that is worth looking at. Hopefully, those who advocate a new software stack, a new systems architecture, will get the buy-in from the OS people that will make it happen. And I hope so. Find first. AMD had one of those, you know, the 80s was the decade of the RISC processors, and AMD's contribution was the 29,000. And they decided for lots of floating point stuff and for lots of system stuff, taking a bit vector and finding out which is the highest bit that is a 1, or which is the highest bit that is a 0, two instructions in the AMD 29,000 ISA, would be a good thing to do. So they introduced that instruction, and you say, okay, how am I going to find the highest bit that is set? Very simple answer. Use a for loop. So I'll shift 1 bit and then examine the end condition code. It's a 0, okay, shift 1 bit, examine the end condition code. And I keep going through that loop, and it's going to take me tens of instructions in order to find that first bit that is set. But how about forgetting a software solution and look at a hardware solution? Finding the first bit set in a bit vector can be handled by a priority generator in a fraction of a single cycle. So why not do that, all right? We have this problem, you know, well, do it in software. No, do it in hardware. In fact, so what do I say? Use a for loop, shift left and check the end bit, tens of clock cycles. Do it in hardware, a priority encoder, less than 1, whoops, that should be 1, O-N-E, 1 cycle. Always a consideration, do it in hardware or do it in software. You know, I spent 9 years teaching at the University of California, and They asked me, what do I want to teach? And I said, I want to teach the data structures course, and I want to teach the computer organization course at the same time. They said, that doesn't make any sense. Data structures is taught by the software faculty. Computer organization is taught by the hardware faculty. Are you a software person or are you a hardware person? So my answer was, what's on the board here, I'm a person. In fact, being in command of both hardware and software will give you an edge at how do we get these jobs done at less energy used and perhaps even higher performance. So this goes back to the VAX days, which was the processor of the 80s, I guess, following the PDP-11 by this Digital Equipment Corporation. And for some artifact, which I don't remember, fetching an instruction took 2 clock cycles. First clock cycle brought in the values, and the second clock cycle cleaned up the mess. And the brilliant engineers at Digital Equipment said, you know, I've got this free cycle. Why don't I guess what those bits are? I just see them, after the first cycle, I just see them as a sequence of zeros and ones. Why don't I say, okay, these zeros and ones relate to this function, I'll do that. These zeros and ones relate to another function, I'll do that. That is, I'll guess, I'll speculate what those bits represent. And if I'm right, I'm ahead of the game. I've just saved the cycle on the execution flow of that instruction. Problem is, the guesses didn't happen correctly very often. So the VAX 11780, the first VAX took an extra cycle to fetch instructions. So why not guess what is fetched and processed just in case? Most of the time you're wrong. So you accomplish nothing, but you wasted energy. So there's an example that made sense in the 1980s, makes absolutely no sense in my view today. Cache trailing edge effect. So Dick Seitz did the first alpha chip, the 21064, and then he was worrying about performance of the next iteration, the 21164. And the 21164 fetched 4 instructions each cycle and delivered a result, the result every 4 cycles. So instead of running at peak, it's running at 4 in, 4 cycles later, 1 out. That's 1/16 of peak. It means that you've got, you're running at 6% of peak. So why? That was his question. So he went and studied the code, and he found that what's happening with the cache. We evict a line and bring in another line. The line is big, takes multiple clock cycles to bring that line in. We access 10% of the line and then kick it out. So the result, 6% of peak. Alpha 21664, 6% of peak. Maybe we need to revisit what line size is all about. Finally, AI, the elephant in the room, and I have no idea what to say about this. AI is requiring more and more energy all the time, and so far we haven't really done anything about it, but we cannot continue the way we are. What we do about it, I've got 4 question marks. Okay, a final point. I admit that I am at the tip of the iceberg right now, and worse yet, not clear how much benefit I'm going to get from each one of these things. What if the whole set of items that I gave you to work on ends up giving you 2% savings in energy? Is it worth doing? I say yes, because our attempts keep the problem in mind. And if we're lucky, we'll get others on the bandwagon, and we'll end up still occupying one planet at the end of the century. Arigato.